Hey, and welcome to this second video from the gathering, where we're looking at the following topic. So we've seen earlier that Lie algebra homomorphisms, they can correspond to a Lie group homomorphism. If the group is simply connected, then we can always integrate this. It may be true for other groups, but we don't know in general. So next we're going to talk about subalgebras of a Lie algebra. So again, Lie algebras, since the vector spaces are generally, and since the operation is linear, generally easy to deal with, generally easier to look for subalgebras than it is to look for subgroups. And then the question is, which of these subalgebras correspond to subgroups of my general matrix Lie group? And right away, we have to realize that we have to expand our definition of what kind of nice subgroups we are thinking of to go beyond the scope of matrix Lie groups. And then you can see the reason for this in the following example. So suppose that our big Lie algebra is GL2C, so all 2x2 complex matrices. Then we look at the subgroup, the subalgebra that we looked on before. So it has I here and IA here, but this A is irrational. And then when we take the exponential of this, we get a rotation here and a rotation here, but these rotations are never in sync. And so for every t, I get a different matrix because of the irrationality of A. And we've seen before that this will not be closed inside the group of invertible matrices in general. So we have a Lie algebra, a subalgebra. So this is just a one-dimensional real abelian subalgebra. Bracket of this matrix with itself is zeros, which is inside the group. And so we have a corresponding subgroup, but it will not be a matrix Lie group. So we have to expand a little bit on how we call what we call a Lie algebra of something. And so we state that, okay, if H is a subgroup and not necessarily a matrix Lie group, its Lie algebra is collection of all matrices satisfying that the exponential at all times is inside of this group. So this is exactly the same definition as before, but what changes? Well, the part that changes is that essentially some of our proofs that we used before no longer work. For example, earlier we showed that the Lie algebra was a vector space by applying this formula here. By using this formula, we show that okay, if x and y were in the Lie algebra, then these two elements, they will always be in G, and then we can use this limit here. As if we were closed, we knew that it was inside a limit, plus works for the Lie algebra. But this is not, we can no longer use this kind of proof, and we need to find go even outside of our book to find the proof. But but these kinds of groups and their Lie algebra will be useful to talk about the correspondence between the subalgebras and subgroups. So we make the following definition. So instead of saying a matrix subgroup, we say a connected Lie subgroup if it satisfies the following. So H is a subgroup of G. Its Lie algebra is a subalgebra of G. So all of these matrices that go inside it does indeed form a subalgebra, and it can be written as products of elements from that subalgebra. So we call that a connected Lie subgroup, and it is connected because that means that I can do T maps to the exponential and then T times each of these elements to connect any element from the identity. And it turns out that if we define, if you look at this larger class of subgroups, then every Lie subalgebra has a corresponding connected Lie subgroup, right? So it's not necessarily closed, but there does exist a corresponding Lie subalgebra. In the special case where we have something called a maximal abelian subalgebra. So what is that? Well, that's an abelian subalgebra which is maximal if it's not contained in any larger subalgebra. So there's no bigger abelian subalgebra that contains it. So if we have such a subalgebra, then our subgroup is closed. And the proof of this is essentially the fact that if we take a Lie group and we close it, then the product of things in the closure is going to be in the closure, and if things commute before we can get commutation by taking the limit, so it will also be commutative, and hence we get a larger group with some Lie algebra, but this Lie algebra cannot be larger because that would strictly larger because that would contradict the maximality of H. And so we have a subgroup contained in this whole closure. Both are connected and abelian. The Lie algebra of one should be inside the Lie algebra of the closure. But since this is maximal, both have to be equal. And then it follows that the groups are equal since they're connected, and hence just product of exponentials. So that's one of the topics that we didn't cover. So the second topic is which kind of Lie algebras are actually matrix Lie algebras. So we saw that, for example, R3 with a cross product is a Lie algebra, but it's isomorphic to a matrix Lie algebra SU2. So the question is this always the case? And the first statement related to this is called Adot's theorem. And it says that if you have a finite dimensional real complex Lie algebra, then it is isomorphic to a subalgebra of GLNC for some n. No matter which kind of finite dimensional Lie algebra you have, you can always see it as a subalgebra of some matrix algebra. And here I'm writing complex, but as we saw during the gathering with complex simplifications, you can always put complex matrices into a larger set of real matrices. And the next statement is that if you have a finite dimensional Lie algebra, then it is the Lie algebra of some connected Lie group here. And the reason for this is that G of matrices, and the reason for this is that this matrix group has this as its Lie algebra, and then our previous theorem, which said that any H corresponds to a connected Lie subgroup, holds here. So that means that any finite dimensional Lie algebra can be considered as the Lie algebra of some matrix, of some Lie group. And then there's a trickier one to actually get to make sure that these are actually closed. You can find one version where they're embedded as closed subgroups, which also is one of these harder theorems, which are where the proof is not really in the book. But it is true that any finite dimensional Lie algebra, there is some matrix Lie group that has this as its Lie algebra. So when it comes to Lie groups, we've seen earlier that there are some Lie groups that are not matrix Lie groups that you cannot put inside the space of matrices, but this is not true for Lie algebras. So any finite dimensional Lie algebra, you can always put inside the space of inside the space of the Lie algebra of general matrices. So you can always see it as a Lie algebra of matrices with the commutator bracket.